Okay. Last class, we learned about some more intermolecular forces. So let's think about what our three intermolecular forces that we have so far are. Remembers what the first one is, one everything has. Dispersion forces. What's our second force? Dipole-dipole forces. What things have dipole-dipole forces? Polar molecules. It's in the name. Dipole-dipole, polar. They're connected. And then our third force is hydrogen bonding. And what things have hydrogen bonding?
Hydrogen bonds with fluorine, oxygen, and nitrogen.
Yeah, hydrogen with fluorine, oxygen, or nitrogen. So dispersion. Everything has dispersion forces. They're very weak. They're temporary dipoles. Dipole-dipole forces. Polar molecules have these. These are permanent. Partial positive, partial negative forces. And hydrogen bonding. Hydrogen bonded directly to fluorine, oxygen, or nitrogen. Those are our first three intermolecular forces. And we also talked about viscosity and surface tension, which are both related to the strength of intermolecular forces. And remember that viscosity is the thickness of a liquid, so things that are higher viscosity are going to flow less smoothly. So we're thinking things like molasses that doesn't pour very well. Cold maple syrup is also going to have relatively high viscosity. Honey has high viscosity. And we're going to sort of take a departure a little bit to talk about melting, freezing, and sublimation, and then we'll talk about some other phases, phase changes after that. So as the temperature of a solid increases, thermal energy, the energy that the molecules, if we're thinking about them as people in a movie theater, the energy that those people in the movie theater have just starts ramping up and they start going crazy as you heat them up. So those are the molecules and the atoms. They're vibrating faster. They're still in their spots. And then at some point you reach the melting point. And that's the point when they're like, we can't sit still any longer. We have to get up and dance to this crazy song that's in the Lego movie or whatever they're doing. Right, so that's the melting point. They have enough energy that they can break away from their neighbors and they start having a mosh pit dance party. They're now in the liquid state. So they can overcome those intermolecular forces that hold them in stationary points, and it turns from a solid into a liquid. We love it when the signal cuts out when I'm only touching things I'm supposed to. And we're back. So melting, when ice melts, solid water melts, the water molecules, wrong tool, the water molecules break free from the solid structure and they turn into a liquid. And now we've got a fun fact. As long as ice, the solid state, and water, the liquid state, are both present, the temperature will be 0 degrees Celsius. I like to say that it's locked in at 0 degrees Celsius. How is this relevant to us? Some people like drinking ice water. Other people, it makes their teeth hurt, and so they don't like necessarily drinking ice water. I'm a room temperature Andy. But for those of you that like drinking ice water, as long as it's staying reasonably well mixed, you're getting a very consistent drinking experience. You are living in a world where all your beverages are 0 degrees Celsius. They're always going to be the same temperature. If you drink your water at room temperature, your beverage is at room temperature, maybe you're a little bit more adventurous. You don't know what you're going to get. It could be 30 degrees Celsius. That would be pretty warm. It could be more like 15 or 10 degrees Celsius, depending on where you got it or how long it's been since the ice melted. So that's kind of fun. This also means that if you've got like your cooling drinks, like you've got people over for a party and you've got an ice chest full of drinks, as long as there's a decent amount of ice in there, you know that your beverages are staying nice and cold. It doesn't have to be absolutely jam-packed with ice to keep it nice and cold. So that ice water is going to be locked in at 0 degrees Celsius until all of the ice has melted. Once all the ice has melted, then additional heating will raise the temperature of the liquid past 0 degrees Celsius. We also have a state change called sublimation, and sublimation is the phase change from a solid directly to a gas. And this isn't something that we typically observe very much, like us in the room don't observe very much. It's happening all the time. It's the reason that you can sometimes smell metals. You're around a lot of metal and you just like, it kind of smells like metal. You're probably actually smelling the metal, or you're smelling things that came off of the metal. When substances sublime, the molecules leave the surface of the solid, they just go straight into the gas phase. So not only are they breaking free from their neighbors to be able to move around or past them, they're also just leaving them behind completely. And they're going to leave from the surface of the solid because the ones that are on the interior have other things around them. They're completely blocked on all sides by other atoms or molecules or formula units, and so they're going to run into those things before they can actually leave. So it's just going to be based on the surface where we see the sublimation. Dry ice or solid carbon dioxide is the go-to example for sublimation. You can actually buy dry ice or solid CO2 if you're 18. I think you can usually buy it at like a grocery store. Sometimes they'll have it for sale. It does not melt at atmospheric pressure at any temperature. There's no temperature in which you get liquid CO2 under normal atmospheric pressure conditions. And at the very cold temperature of minus 78 degrees Celsius, those CO2 molecules have enough energy that they just leave, they turn into a gas. And what this looks like, if you put a piece of dry ice into water, is you get vigorous bubbling. It's absorbing tons of energy from the water. It bubbles very vigorously, and then eventually there's enough frozen ice on the outside of it, like liquid ice, water ice, that it stops doing that quite as much. And here's an example. Here's a picture of somebody that put some dry ice into a bowl. Presumably they added a little bit of water. So sometimes like Halloween parties, you want to make a spooky like fruit punch bowl. You add a little bit of dry ice to it, and now it looks really spooky, especially if you've got some red or orange lights and some other themed decorations. So you're never going to see liquid carbon dioxide under normal atmospheric pressure. Other fun stuff that you can do if you do get your hands on dry ice, if you go and buy some for some reason. It's not going to keep in your freezer, so I wouldn't recommend trying to keep it around because your freezer's not cold enough. You can add it to things, and then if you seal them, don't do this in glass containers because they'll explode. If you seal them for a little bit, that dry ice is going to turn into a gas, and some of that will get absorbed into the drink, wherever the liquid is, and that will carbonate it. So you can carbonate stuff at home with dry ice, but again, if you take a little bit of dry ice, 44 grams is about 1 mole. Let's make those squiggly so it's about 1 mole of CO2. Yeah. And 1 mole is about 22.4 liters. So if you're putting a relatively small chunk of dry ice into a container, 22.4 liters of gas comes out. That's going to create a lot of pressure. You could do the calculations for that if you know the size of the container. And if it's glass, it might explode, and that is obviously bad for you if you're nearby. Also, something that I've been dying for somebody to try, but nobody has taken me up on this offer yet. I think it would be really interesting. I'm sure there's videos of it online, but I'd love to hear somebody's experience. If you take some dry ice and you add it to some milk, and you carbonate the milk, like you got to drink it right away because I think it'll curdle. It might curdle. I'm not 100% sure on that, but I just think that would be a silly experiment to try. So if you ever get your hands on some dry ice, maybe in like a plastic bottle, definitely not a metal bottle, but maybe a plastic bottle, make a little bit of carbonated milk and see how it tastes. But don't sue me if it goes really badly. Regular ice will also sublime at temperatures that are below 0 degrees Celsius. Remember, 0 degrees Celsius is the freezing point of water. It's also the melting point. Just depends on what direction you're going. But if you're below that, then it should be a solid. But regular ice, like you have in your fridge, will also slowly sublime out of whatever it is in at those temperatures below 0 degrees Celsius. So even in really cold climates, if you've got ice or snow lying on the ground, it will gradually disappear even if your temperature is below 0 degrees Celsius. So places like if you go up into the mountains, if you go back east, anywhere where we actually get snow, if you go to Antarctica, the snow that's lying out from whatever last snowstorm, even if it stayed at like minus 40 Celsius, super cold outside that whole time, some of that ice and snow is subliming. It's turning into the gas phase and it's leaving. So if there's not new snow that's added on, you'll eventually run out of snow or ice that's on the surface. This also, more applicable to us, applies to things like ice cubes. So ice cubes left in the freezer also become smaller, even though the freezer is hopefully always below 0 degrees Celsius. This is why if you make, like if you got the ice cube trays at home and you just don't use very much ice, you're like, ooh, this would be a perfect opportunity to have a nice cold beverage because it's warm outside today. You go into the fridge and you pull out your ice tray and it's just like the freakiest ice you've ever seen. It's all pulled away from the sides of the containers and it's like weird and misshapen. That's because it's just been sitting in there long enough. Some of those ice molecules have left. We expect them to be nice, maybe square shapes. So this is our expectation, right? They're nice and square or they're nice and rectangular. And then we get in there and it's just like a weird little tooth-looking thing. I don't know if you've ever had that happen to me. Obviously, you can tell that's happened to me a couple of times. This is not related to the ice cubes that have the little like finger poking out of them. That's a different thing. So this can happen to ice cubes that are in your freezer. It also happens to frozen food. So ice also sublimes out of frozen food. And if ice is leaving, ice is another form of water. So if water is leaving, what happens to the food? If water is leaving the food, what's happening to the food? It dehydrates or dries out. A lot of this stuff is just fun, practical applications where you can see chemistry in your daily life, which is like my favorite part, so we're going to spend too much time on this. So if you buy like frozen peas or frozen mixed vegetables or something else like that, there are ice crystals that are in the food, frozen water inside of the food. And over time, you're going to get ice crystals that form on the inside of, if they're in a plastic bag, they're going to form on the surface of the plastic bag on the inside. Those ice crystals are water that has sublimed out of your food and redeposited on the surface of the bag because it was stuck in that container, but it got out of the food and it froze itself onto the container. And then you go to make your peas or whatever frozen food you've got, and it's all dried out because it's lost all of that water from the inside. That is freezer burn. Or if it's not, nobody's corrected me yet. And a way that you can avoid freezer burn is by freezing foods at colder temperatures, like with a deep freezer. So if you're somebody that goes out and hunts, and you've got a big chest freezer in your garage or somewhere else, hopefully it's storing at even lower temperatures than like the freezer in your house. And so things that you throw in there, or you vacuum seal them, things that you throw in there are going to stay good longer because they don't have time to accumulate as much freezer burn because they're at colder temperatures. So the water's leaving less, and so your food stays good for longer periods of time. Lower temp equals slower sublimation. There's also another place that I'd like to talk about where this sublimation process happens. How many people like ice cream? We got a lot of not ice cream lovers in the class, which is crazy. Anyway, I like ice cream. I love Tillamook ice cream. I'm not sponsored by them, but that'd be cool. Crazy to have a teacher sponsored by Tillamook ice cream. It's my favorite ice cream. Sometimes I'm just not in the mood for ice cream for an extended period of time for whatever reason. But I've got ice cream in the freezer, and then, you're like, ooh, I've got ice cream in the freezer. You remember, you run to the freezer, you pull the ice cream out, you get the scoop, you open the lid, and there's ice crystals all over the inside of the lid. And I know from experience, I'm in for a bad time. The texture's going to be wrong. It's not going to be nice and creamy. It's going to be sort of like clay, putty. There will be chocolate. There will be, peanut butter in there still, but it's going to feel weird on the mouth. Freezer burn. So this is my favorite application for the class. The lesson that we're learning here is you have to eat your ice cream before it goes bad. So make sure that you're eating your ice cream. All right, enough about sublimation. Did anyone have questions about sublimation, melting, or freezing? We will talk about them more with like heat exchange and stuff. All right, some other phase changes. Evaporation, also called vaporization, is the change from a liquid to a gas. So this is what we normally expect to happen after something changes from a solid. We expect it to go from a solid to a liquid and then to a gas rather than from a solid directly to a gas. We also have condensation up at the top, which is just the opposite direction, gas to liquid. My expectation, I don't know if you'll actually be tested on these, because I don't remember if I normally put questions on them, but my expectation is that you know all of the names for our different phase changes. So you should know freezing, melting, sublimation, evaporation or vaporization, and condensation. You should know what those words are. You should be able to identify which of those words matches up with the definition that's related to the phase changes. Some things that affect the rate of vaporization or evaporation. We're going to box this in blue. These are good to know. The rate of vaporization, so how quickly something goes from a liquid to a gas. How quickly something evaporates. Changes with a couple of things, a couple of factors. Increasing surface area. So if your liquid is really spread out, that's going to increase your rate of vaporization. If something has increased temperature, if the temperature goes up, that's also going to increase the rate of vaporization. So if it's hot, then it will also evaporate faster than the cold version. And decreasing the strength of intermolecular forces, this isn't really something that you would change for a specific chemical, but if we're comparing two different chemicals like water versus acetone, the one that's got the weaker intermolecular forces will evaporate more quickly. So weak intermolecular forces will be faster. Think the alcohol in hand sanitizer versus just regular old water. If you go and wash your hands and you have water on your hands from washing your hands, and you just I'll just wait for them to air dry, and then you leave, and then it's 15 minutes later and your hands are still wet. Versus you get hand sanitizer on your hands, you rub it all over your hands. You're doing a couple of things there. You're increasing the surface area, so you're spreading the hand sanitizer over your hands. It's also got decreased strength of intermolecular forces because it's alcohols, it's not water. And so the hand sanitizer is going to evaporate. It's going to dry out a lot more quickly. Liquids that evaporate easily are termed volatile. Things that do not vaporize easily are termed non-volatile. In my head, this is all like with the reference point of water. If it evaporates more easily than water, then it would be volatile. If it's less or about the same as water, then it would be non-volatile. I don't know that there's like a universal international standard, but it could be water. We can just say that it is. Let's look at what happens with evaporation. So this is an image of what happens during evaporation. So we've got down here this whole bottom section. This is our liquid area. You can see all of our molecules are held closely to each other. They're touchingly close. They could reach out and interact with their neighbors when they're down here. Up in the top, we've got our gas phase, and they're all separated by lots of empty space. In a liquid, the molecules that are on the surface, these are the ones that are only held by their neighbors, and they're also held down. We were talking about this with surface tension. Because they're not held in all 360 degrees in all directions, if they get enough energy, they just have to break away from the things that are next to them and below them. So it takes a little bit less energy for them to eject versus like something that's in the middle would have to work its way out to the surface and then get ejected. And since all of these molecules or atoms, whatever they are randomly bouncing around, it's possible that, like for this little dude here, it's possible that like 3 of their neighbors all happen to hit this molecule at about the same time, and each of those hits transfers some energy, and then boom, they get sent out of the liquid. They've got a bunch of energy now all of a sudden, and then they leave, and they take all of the energy that these liquid molecules gave it, so now these molecules are poor in terms of energy, and the money goes with the molecule that left. So this is happening even for things that are like at room temperature. This evaporation process is happening. And because these took energy away, the temperature of the liquid decreases as a result of the evaporation. Any questions about evaporation so far? So a couple of ways we can affect evaporation. If we want to speed it up, we can spread it out, we can heat it up, we can decrease the intermolecular forces. At any given temperature, a sample of molecules or atoms is going to have a distribution of kinetic energies. There's going to be a range of different kinetic energies. Some are going to be low energy, lots will be middle energy, and some will also be high energy. If you're familiar with distributions, if you've taken a stats class, you've seen the normal distribution, that's sort of what we've got going on here. It's not quite normal. It's usually a little skewed one way or the other. Lots of people are going to be in the middle. Lots of molecules are going to be in the middle. Some people will be on the low side. Some molecules will be like low energy. Some molecules will be high energy. And the amount of energy that they need to escape just depends. But generally, we can reference this graph. This is one of my favorite graphs. On the x-axis, we have energy. So as we're moving left to right, we're increasing the energy. So things that are over here on the left side are going to be really low energy, low temperature, we might think, but individual molecules. On the right side, we're thinking these are molecules that have high energy. And then on the y-axis, we've got the number of molecules. So the taller it is at that point, the more molecules we have at that energy state. And we're comparing two different temperature values here. So we've got T1 is the blue line, and this is our cold sample. This is a cold liquid. Most of the energy, or most of the molecules, are low energy. or lower on our energy scale based on how we've got it drawn out. If you heat it up from cold to a little bit warmer, now our peak has shifted over. So rather than most of our molecules being lower energy, they're now a little bit higher energy. Our peak has also moved forward. And then if they get enough energy, if they're on the high energy side, we've got this threshold energy. This is the energy to evaporate. So anything that's above this evaporation line can turn from the liquid into the gas. If we look at our cold sample with the blue, in our cold sample, our cold temperature, we've got just this small little tail area up in the front. When we heat it up, our distribution has changed. It's shifted to the right. And now we've got all of these additional, all this red zone. We've got all of those last 20 yards that have enough energy that they can also escape. And essentially all that I'm showing you here is that as temperature increases, we go from low temperature to high temperature, the amount of molecules that have enough energy to release from the surface and turn into the gas also increases. And this is why, like, if you go to a restaurant or you're at home and you microwave some soup, somebody gives you some hot soup, the steam that's coming off of it is an indication to you, we've probably mostly learned this, that means it's hot, right? The steam that's coming off of soup or like a glass of tea or coffee, cup of, means it's hot, right? Cold, if somebody serves you iced tea and there's like smoke coming off, the like vapor coming off, that's not what's supposed to happen, right? So that's there's some warning bells. And then the opposite process is condensation. Condensation is our physical change from the gas state to the liquid state. So this is opposite to evaporation. There's also a special state that we can reach. It's not nirvana here. That's a different state. When the rates of condensation and evaporation are equal, that's called dynamic equilibrium. So dynamic equilibrium, evaporation rate equals condensation rate. So for every molecule that evaporates, there's another molecule that condenses. So they're going in opposite directions at the same rate. And what this effectively does is makes the number of gaseous molecules remain constant. Because for every molecule that condenses, one's going to evaporate. For every molecule that evaporates, one is going to condense. If we represent them with arrows, they're nice and balanced. Anytime that you're not at dynamic equilibrium, you're going to either have more evaporation or you're going to have more condensation. Once you reach dynamic equilibrium and these evaporation and condensation rates are the same, then you can measure what's called vapor pressure. Vapor pressure is the partial pressure of a vapor in dynamic equilibrium with its liquid. Oftentimes we ignore the dynamic equilibrium part, or I feel like I often ignore the dynamic equilibrium part, but it is important. So vapor pressure is the partial pressure of gas at equilibrium. So once you've given it enough time that those evaporation and condensation rates equal out, that's when we can measure the partial pressure. I believe we did this last week when we were making the hydrogen gas in the little reaction vessels. That table that we used to figure out what's the partial pressure of the water vapor, that was based on vapor pressure. That's that pressure, what it was. Vapor pressure changes with two things. Vapor pressure changes with increasing temperature and decreasing strength of intermolecular forces. I'm going to actually delete that. So this looks similar to the things that increase the rate of evaporation, but we only have two things instead of three things. We've got increasing temperature. So if we have a higher temperature, we're going to have more gas. We've increased the temperature so that now it's easier for those water molecules or whatever molecules to enter into the gas phase. This is like if we look at this graph, right? We go from this blue line distribution, this low energy, low temperature. We've got this many particles, whatever this area is. If we increase the temperature, now we're adding all of these molecules in as well. And if we increase the number of moles, that's going to increase the pressure. So if we move to a higher temperature, we're going to get more gas. And decreasing strength of intermolecular forces will also increase the vapor pressure because it's easier for those molecules to leave and turn into a gas. Vapor pressure is independent of surface area. Surface area affects the rate of evaporation, but it also affects the rate of condensation. So if we increase the surface area, that's going to increase where we can evaporate, but it's also going to increase where we can condense. And so those two forces end up canceling out. It affects those equally. And we will briefly look at an example of establishing that dynamic equilibrium. So we've got three different snapshots from a process that's happening. In frame one, we've got water in a sealed container. So this is like you just filled up your water bottle. You can actually see this if you do it with like a clear water bottle. It's a little bit slow and honestly a little boring, but if you do it with warm water, you'll see it faster. So water in your sealed container is going to begin evaporating once you put it in there. Over time, because there's so many water molecules evaporating, eventually some of those are going to condense on the walls. So you'll start to see, if it's a clear water bottle, you'll start to see water droplets forming on the sides of your water bottle container. And then those will eventually, once they get big enough, those will drop back down into the main body of the water. And eventually those rates are going to equal out, and you'll no longer see the number of like the water on the sides increasing. It's just going to kind of roughly look the same the whole time. So that's the rates of evaporation and condensation sort of balancing out. Any questions about evaporation or condensation? How many of you have been to a basketball game and you see somebody fall, and it's at like a high school level and not a nice high school, not like a super fancy high school? Because at fancy high schools, when somebody falls down, obviously everyone picks them up, but then somebody comes out with like a special looking like Swiffer thing, and then they just walk over the area where they fell down. Do we know why they do that? To clean up the sweat, because sweat on a smooth floor is going to be very slippery. So if they're not fancy, if they don't have the money for the special Swiffer to pick up the sweat, do we know what the players do? They might use a towel, or sometimes all the players come around and they kick the ground, and there's all the squeaking sounds. They kick the ground where the person fell down. Why are they doing that? Is it to disrespect who fell down? No, it's not. It's for the same reason as they bring out the fancy little broom. But they're kicking their feet on the ground. And what they're doing when they do that Let's go back to our evaporation slide. What they're doing when they do that is they're spreading out the sweat, the water, on their shoes. So that increases the surface area. There's also some friction from kicking the ground like that, because basketball shoes tend to be pretty grippy. So there's also some increasing temperature that's going on with that as well. And so that's going to cause that sweat area to spread out, heat up, and then dry out so that it's no longer slippery. You don't get somebody else that comes running through and it looks like they stepped on a banana peel. So that's what's going on when they do that at a basketball game. The rate of vaporization increase here also is helpful for drying our hands. So lots of us, probably lots of us, the hand dryers, not the fancy like Dyson ones where you you look like you're DJing a set. When you're drying your hands, you just put them in and out. The like regular ones where you have to rub them together. Most of us have probably had the experience of it takes too long. I'm just going to let it blow most of the water off and then I'll just dry them out on my pants. I'm guessing that a lot of us have had that experience. And that's simply because we weren't equipped. Nobody told us the secrets. So I'm going to tell you the secrets. We can increase the rate of vaporization with increasing surface area. When your hands are under the blow dryer, some of those areas on your hands are going to be dry. You'll have some water droplets. If you rub your hands together to spread that moisture out, that's going to increase your surface area. That's going to cause them to dry out a lot faster. And then obviously, increasing temperature, this is why they tend to get really hot. They blow hot air, ideally. That's to help the water evaporate as well. So if you're blow drying your hands, if you rub them together, it's so much faster than if you just like stick them there and wait for it to blow all the water off. You can actually get it to dry your hands so you don't have to rub, have water spots all over your pants or your shirt. So that's another takeaway that I like from this section. All right, on to boiling. Boiling is when a water is changing from a liquid to a gas. When we're heating it up, it's gotten to the point where it can now go from a liquid into the gas phase. This is the temperature at which the vapor pressure of the liquid is equal to the pressure above it, and this will cause it to sort of spontaneously, just randomly change from a liquid to a gas. When we're boiling water at home to make pasta or whatever food we might be making boiling, this is when all those bubbles start to form. Not the initial burst of bubbles, but once they're like really, really starting to form and show up in our pot of water. So at the boiling point, the thermal energy is enough that the water molecules in the interior of the liquid can become gaseous. So that's why you see bubbles form on the inside rather than just the steam rising off the surface of the water. This has a couple of ways that this can change. So because it's the temperature that the vapor pressure is equal to the pressure above it, if the pressure, which is lower at higher elevation, if the pressure drops, you don't have to heat the water up quite as much to get up to match that pressure. And so practically what this means is that boiling point is lower at higher elevation. Water boils below 100 degrees Celsius at higher elevations. So if you go backpacking, if you buy backpacking food, sometimes if it's like, hey, add boiling water and then cook it for this amount of time, or boil for this amount of time, sometimes those packets will have on them, if you're at this elevation, if you're at like 7,000 feet, add 5 minutes to the cook time. For every 7,000 feet above that, add another 5 minutes, or every 1,000 feet, add another minute. That's because the boiling point is lower. So it won't be able to get up to 100 degrees Celsius, and so you're going to be cooking at like maybe 96 degrees Celsius or 95 degrees Celsius instead. We're pretty close to sea level. We're at like 400 feet of elevation. So our boiling point is about the same as the 100 degrees Celsius boiling point. So if we're cooking pasta, you just read the instructions on the box, you cook it for that amount of time, and you get nice al dente pasta, or maybe you like soft pasta, and so you cook it longer. If you were in Denver, the Mile High City, they're at a higher elevation, the boiling temperature is going to be lower, and so you're always going to have to add a little bit of time on anytime you cook something in boiling water. Once you get to the boiling point of a liquid, the boiling temperature of a liquid, extra heating only causes more rapid boiling. Just like with our freezing point, the temperature is locked in. It is not going to move. You can get water up to its boiling point. You cannot get it hotter than that until it's turned into steam, and then it can get as hot as you want it to. So if the pot's boiling, a rapid boil and a not rapid boil, just like a trickle of bubbles, is going to be about the same in terms of cooking temperature. If you boil it faster and you've got to boil it for a long time, there's a good chance that you might just run out of water. And then you're going to be really sad because you're going to have burnt stuff in your pot. Once all the water has been converted to steam, the temperature of the steam can rise beyond 100 degrees Celsius. Another thing that's cool about this temperature being locked in for boiling water is if you've ever made pasta and you've thought to yourself, why am I setting a timer and not checking the temperature? Do you ever think about that? It says boil for 7 to 8 minutes, and you just set a timer. You don't ever check, is the water hot? Is it at a certain temperature? Like if you're cooking meat, you want to check the temperature of the meat. You're not going to, your dad or your mom, whoever does the meat management in your household, is not going to say, yeah, just throw it on the grill for 10 minutes and then take it off and it'll be done. Because what if the flame's too hot? What if it's not hot enough? There's lots of factors. But when you're boiling something, the temperature is locked in, so you just set a timer. You know it's going to be at that temperature, and so you're going to get basically the same consistent experience every single time. So that's kind of fun and magical. There's also some energy changes associated with melting, freezing, boiling, condensing. Adding ice cools a drink because melting is endothermic. Endothermic means it's absorbing energy. So you add cold ice to room temperature water, and there's going to be heat transfer from the water to the ice. That makes the water cool down, and the ice heats up. It does a little bit of melting. So melting is endothermic because the energy required to partially overcome the attractions, to get them from locked in their spots to moving past their neighbors, that takes energy. Freezing, on the other hand, is exothermic. When you freeze something, it releases energy. Heat is released when a liquid freezes into a solid, which is not what we expect. So if I ask you a question about is freezing exothermic or endothermic, you might think, oh, it's endothermic because it's getting colder. It's exothermic because it's losing heat to get colder. You can also think about the opposite. If you think about freezing as you're not sure what it is, if you think about melting, in order to melt, it has to absorb heat to increase the temperature. So the opposite is going to be true. Freezing is going to lose heat to happen. And the way that your freezer does this, water in your freezer, when it turns into ice, releases heat. So what your freezer compartment does, or if you have a dedicated freezer, through the power of physics, it's pumping all of the heat out of your freezer compartment, or a lot of the heat out of your freezer compartment, and then where does it go? Into wherever your freezer is. This is also the same thing that happens with air conditioning. If you've got an air conditioning unit just sitting in the middle of the room, like circulating the room around, yes, some of the air that's coming out is colder, but the rest of that heat has to go somewhere, and it's just going to go back into the room. This is why you usually have, like if you've got air conditioning, usually the unit's mounted on the outside of the house. It just dumps heat outside from the inside. Takes heat from inside, dumps it outside. Sometimes they're set up, they can do it the other direction as well. So usually the area around fridges and freezers, there's like a specified, it has to have this much space around it because it's dumping heat, and that heat needs to get out and go somewhere. What was the other thing I was going to say? Oh, my favorite, one of my favorite little graphs to make. It's a one-axis graph, and our axis here is energy / temperature. Let's call it temperature. What's our coldest phase of matter? It's our lowest energy state of matter. Solid. What's higher energy than solid? Liquid. What's higher energy than liquid? Gas. So if we are melting, what phases are we switching between? Solid to liquid. So if we're going from a low energy phase to a higher energy phase, do we need to gain energy or lose energy? If we're going from a low energy to high energy, do we have to put energy in? Do we have to take energy out to get it to do that? You'd have to put energy in. So melting requires energy input. That's why it's exothermic, or endothermic, sorry. If we're doing freezing, we're going from, let me just copy this. If we're freezing, we're going from a liquid to a solid. So we're going from a higher energy state of matter to a lower energy state of matter. To decrease our temperature, we would have to get rid of some energy. We'd have to lose energy, which is why freezing is exothermic. It needs to lose energy / temperature / heat. This works for all of the phases, all the state changes. You can make this one simple graph. Think about what phase am I starting in, what phase am I going to? Do I have to put energy in to do that? Do I have to take energy out to do that? Is it going up in energy? Is it going down in energy? That's part of why I like it. It's a really simple graph. All right, there are energy changes associated. So we've been talking just about the concepts, our different state changes, what's happening with the energy, a little bit with them. What are some fun facts about them? The fun facts don't show up on exams. Those are just for you to keep for fun. But there's also some math. We also get to do some math with them. So we've got some heat quantities. Our first heat quantity that we're going to talk about is the heat of fusion. And fusion is freezing or melting. It's the heat associated with those two phase changes. So our heat of fusion, we get delta H, change in heat. And then the FUS part does not stand for fusilli pasta, it stands for fusion. I had pasta last night, it was good. The heat of fusion is the amount of heat required to melt 1 mole of a solid. It's always going to be per mole. And we can show this as a reaction. We're going from a solid to a liquid, and our delta H, our change in heat, is we add in 6.02 kilojoules, and then the secret per mole. So let's say that we're melting 2 moles of ice. how much heat is absorbed. This change from a solid to a liquid is per mole, 6.02 kilojoules per 1 mole. We have 2 moles. So we're going to multiply the number of moles by our kilojoules per mole. The mole parts cancel. We get 12.0 kilojoules. Let me get 2.00. So the sig figs work out. Typically, we're not just going to say, here's how many moles you have, how much heat does it take. Oftentimes, there will be a grams to moles conversion, so you'll also have to either calculate a molar mass, or maybe if I'm feeling really nice when I made the exam, I'll give you the molar mass. The same amount of heat is involved when 1 mole of liquid water freezes, but the heat is emitted rather than absorbed. So this negative means heat is released, / lost, / emitted, whichever of those you like best. But the number is the same. So this is the same number as melting. It's just negative now because we flipped the left side and the right side. Okay, so we can use the heat of fusion to calculate the amount of heat energy required to melt a given amount of solid. Heat of fusion, delta H, converts between moles and heat, kilojoules or joules, usually. It's not always kilojoules or joules. There's other energy units that we can use instead. Oftentimes, it's going to be in those units, though. Which unit is bigger, kilojoule or joule? Kilojoule. One kilojoule is 1,000 joules because the kilo prefix means 1,000. Kilojoule is bigger. If you tell somebody, hey, I ran 5 meters, whoop-de-doo. For most people. Some people that might be an accomplishment. If you tell your friend, hey, I ran a 5K, I ran 5 kilometers, that's probably for most people a bit more impressive. That's like 3.1 miles. Kilometers are bigger than meters. All right, example problem. Calculate the amount of heat absorbed when a 25.4 gram ice cube melts. The heat of fusion is given. 25.4 gram ice cube melts. Usually we're going to specify that it's at the freezing point or it's at the boiling point because they're slightly different depending on what the temperature is. Heat of fusion at 0, left a 0 out, is that number. So we're given 2 different pieces of information. What are we trying to find? We're trying to find amount of heat. We're told that it's absorbed. What's a unit of heat? joules or kilojoules? I'm going to use kilojoules here because it shows up in our heat of fusion. Do we have something that we can use to convert to kilojoules? The 6.02 kilojoules per mole. It's got kilojoules in there. It's got another unit in there that makes it a conversion factor. They're on opposite sides. So we could get to kilojoules using our 6.02 kilojoules per mole. We write the 1 mole part on the bottom. That makes it even more clear that it's a conversion factor. What would we have to get to kilojoules using this conversion factor? Moles. Do we have moles? I do. I've got 2 in my office. Sorry, do we have moles in the problem? No, we don't have moles. Can we get moles? We sure can. How do we get moles? We convert from our 25.4 grams of water. What do we need to do that conversion from grams to moles? We need the molar mass of water, which is 18.015. So that's what our solution map is going to look like for this problem. So starting with our 25.4 grams H2O. By the way, if you're confused about where did we get that 18.015 grams per mole, I've seen it enough times that I just have it memorized. If you're confused about how would I get that though, go see Logan in his SI sessions. He'd love to go over how to come up with molar masses from the periodic table with you. All right, so we've got grams of H2O. Our molar mass is grams of H2O over moles of H2O. We want to get rid of the grams. We've got to flip our molar mass. Flip. Top goes to the bottom, bottom goes to the top. The grams of H2O cancel. Now we've got units of moles H2O. We've got moles on the bottom in our delta H. So if we multiply by our delta H, the moles will stay on the bottom, and that'll cancel out with the moles that we have. The kilojoules will come out. So we're multiplying by 6.02 kilojoules. This is per 1 mole. The chemical would be H2O. Moles H2O cancel, and what we put into our calculator is 25.4 divided by 18.015 times 6.02. Or you multiply everything on top, hit enter, gets you a number, and then you divide that by 18.015. And you should end up with 8.49, because the number after the 8 that was there is a 7, so it rounds up. 8 rounds up to 9, and it's 8.49 kilojoules of heat. There is something tricky that can happen with these delta H problems. And that has to do with if it's asking you for the amount of heat or if it's asking you with some directional language like absorbed or emitted. In this case, it's asking us how much was absorbed. It's going from solid ice to liquid ice because it's melting. Solid to liquid. And if we make our little silly one-axis graph, solids are low energy, above that is liquid. So it does have to go up in energy, it has to absorb energy. Absorbing energy has a positive or negative sign for heat. Positive because it's going up, it's increasing. So if we're asked not for the amount that was absorbed, but just for the amount of heat, it is going to be a positive number here because we're going up on our little temperature axis. Sometimes, though, it'll ask for how much is emitted, or it might ask just what's the total amount of heat change. And if it's going from the liquid to the solid, there'd be an arrow pointing down, and you would end up with a negative number. So sometimes this sign stuff can be a little tricky. If we see more examples, I don't remember if I've got those in the slides. If we see examples, I'll be sure to mention them. I think there are some that show up on the homework for this chapter, so you'll get to experience them there as well. We can hopefully work out any bugs and confusion before it shows up on an exam. All right, moving on to evaporation. Evaporation is endothermic. We're going from a liquid to a gas. That's going up on our little temperature axis. So if you're evaporating, the system has to absorb heat to get enough energy to break away completely from your neighbors. You're not just being able to move past your neighbors, you're breaking away from your neighbors. And this endothermic nature of evaporation for cooling is very useful to us as sweaty human beings, as hot human beings in the physical temperature sense, hot human beings. As sweat evaporates, it absorbs heat from our bodies. There's a net loss of heat for our bodies, and that cools us down. A breeze intensifies that cooling effect. A breeze blowing also intensifies the cooling effect that your soup experiences if you're eating hot, hopefully good soup. If you're in a high humidity situation, that's going to slow down evaporation. High humidity slows evaporation because there's less room for water vapor in the air. The percent relative humidity is how much of the water in the air compared to our capacity, how much do we have? So like 10%, that means there's 90% availability. There's not very much water in the air. If you're at 90%, there's only 10% availability. The air is mostly full of water. There's not really much room to put any more in there. And that slows down cooling quite a bit. So when the air already contains high amounts of water vapor, sweat does not evaporate as easily, making our cooling system less efficient. So our fun fact takeaway: sweating cools you down less in high humidity. And we have a phrase for that talks about this phenomenon. But it's a dry heat. You've probably heard that. Somebody said, oh yeah, it's 115 degrees outside, but it's a dry heat. I don't know why I got like slightly Canadian there. Right, 115 degrees, oh, but it's a dry heat. Because our relative humidity is low, and so when we sweat, if it's 110 degrees outside and you're standing in the shade and you're sweating like whatever you'd like to compare yourself to, that sweat actually evaporates and it cools you down. If you've been somewhere with high humidity, Florida is a great example, probably most of the South. If the humidity is really high, your sweat doesn't evaporate, and so you just stay hot and sweaty and gross. It doesn't actually really cool you down. And so like 90 degrees Fahrenheit, if it's high humidity, feels a lot worse, if you're accustomed to dry heat, feels a lot worse than our 110 degrees heat because your sweat doesn't cool you down as well. Another fun fact about the cooling down stuff, there's those like towels that you wet them and you snap them and they evaporate and they're cooling. That's just taking advantage of evaporation. There's no like special chemicals involved. Your forearms are really generally very vascular areas of your body compared to the rest of your body. So if you're ever really hot, you cover your forearms in water and that'll help cool you down faster as well. All right, condensation is the opposite of evaporation. Condensation, we're going from gas to a liquid. So we need to emit / lose energy to go from a gas to a liquid. So condensation is exothermic. Heat is released when a gas condenses to a liquid. This is part of the reason why a covered pot boils faster than an uncovered pot, because you get condensation on the lid that keeps some of the energy in. If you don't have the lid there, the water that evaporates just takes all of its energy with it. You're losing all that energy. This is one of the reasons also why steam causes really bad burns. As steam condenses to a liquid on your skin, it releases heat without changing its temperature. We'd call that latent heat, and that can cause a severe burn. It releases a lot of heat. The exothermic nature of condensation is also one reason why overnight temperatures don't get as low when humidity is high, because you've got water condensing and forming dew on your car, on the grass, wherever it forms. And that process, even though the temperature doesn't change, because it's changing states, it's releasing a lot of heat, and that kind of guards against the temperature changing. It doesn't drop quite as much. Just like we had with freezing and melting, with heat of fusion, we also have got one for vaporization and condensation. It's our heat of vaporization. So this works for vaporization and condensation. The slides are going to look pretty similar. It's the same general idea. So we've got heat of vaporization, delta H. Delta H is the heat of part, and then vaporization we shorten to VAP. So delta H VAP. This is the amount of heat required to vaporize 1 mole of liquid, so it's still per 1 mole. The heat of vaporization of water at its normal boiling point is 40.7 kilojoules per mole. We've got our little reaction diagram. We're going from a liquid to a gas. You've got to put in 40.7 kilojoules per mole to turn it from a liquid to a higher energy, higher temperature gas. Who remembers what the delta H was roughly for delta H of fusion? Melting, freezing. 6.02, which is smaller or bigger than 40.7? Smaller, way smaller. Right? This is like 7 times that amount. It's way bigger because you have to break away from all of your neighbors to leave to evaporate, rather than just being able to move past them. So you're overcoming a lot more ties when you are evaporating. The same amount of heat is involved when 1 mole of gas condenses, as we saw with fusion and melting, but the sign is negative. So the only change is that the sign flipped. And now our delta H is negative. Condensation is exothermic. We're going from a gas to a solid. And that requires that we emit or lose or give off energy. You don't have to memorize delta H values, by the way. Delta H values will be given if needed. So just like we did with our heat of fusion, with our heat of vaporization, we can calculate the amount of heat energy to vaporize a liquid. We're going to use it as a conversion factor between moles and amount of heat, just like we did for delta H of fusion. Calculate for me, please, the heat in kilojoules required to vaporize 1.75 kilograms of water at its boiling point. The heat of vaporization at the boiling point is 40.7 kilojoules per mole. All right. We are looking for what? The amount of heat in kilojoules. We are given what? 1.75 kilograms of water. And what else?
40.7 kilojoules per mole.
Yeah, the heat of vaporization is 40.7 kilojoules per mole. These calculations are going to be almost identical to what we did for delta H of fusion. The one thing that's different here, two things technically, right? Our delta H is different, it's a different number. But we're also starting with kilograms instead of, in the last problem that we did, we started in grams. So we have an extra conversion to do. So starting with our kilograms, we want to get that turned into grams. Kilo is 1,000. So 1 kilogram equals 1,000 grams. Once we're in grams, it's the same solution map as before. We can use our molar mass to convert to moles. And then from moles, we can use our delta H of 40.7 to convert to kilojoules. So our whole solution map would look like this. 1.75 kilograms. We want to convert to grams. Grams are smaller. There's 1,000 of them in 1 kilogram. So we multiply by 1,000. That'll turn our 1.75 into 1,750. Then we're going to divide by our molar mass. That will get the grams to cancel out. And then we can finally multiply by our delta H, or 40.7 kilojoules per mole. Moles cancel, and you should get something like 3,950 kilojoules after you round it off for 3 significant figures, or 3.95 times 10 to the 3 kilojoules. Questions? There's also fun stuff that we could do, like this bonus problem that we're not going to do today. But this, if you want to try it, uses Q equals MCAT. And we can also do fun stuff like these heating curves, which this one unfortunately has all the answers already written in. So we can look at like the time that you're heating water and what its temperature is like. And we can see when we're starting from ice, initially we have to heat up the ice. Once it gets to its melting point though, that temperature locks in for a period of time. Once it's all converted into liquid, now it turns into just its heating liquid. The temperature is going up again. Once it gets to boiling point, then it takes a long time for that to vaporize. You've got both liquid and vapor or gas, water vapor. And then once it's all turned into steam, then we can finally start heating it up again. And we've also got this demon of a problem that we could solve, but we're going to skip that. And we'll pick up next time on solutions.